All right. A couple things I want to review before we get started today. Um, maybe. So if we're doing a cutting operation, so this is a review material now. If we're doing a cutting operation, I've now tucked my shirt into my pocket by clipping it into the thing. Try one more time. We're going to do a cutting operation. And so let's say we've got our workpiece in a vise. So top-down view, I got a vise jaw here. I got a vise jaw here. There's front of the vise, the back of the vise. We've got our handle out here. Side view, we'll look at the end of the vise maybe. All right, so I've got my thing there. The jaws stick out a little bit wider and they're a little bit taller. And my workpiece is up here like this. Right, so we're looking at it, and so let's say our work zero is in the center on the top. Now, what keeps the part from flying up out of the vise if we have cutting forces that are pulling in the upward direction? Friction, right? So now, not all the cutting forces will point in the upward direction, though, correct? Some of the cutting forces will be trying to point sideways. Some of the cutting forces, like in a drilling operation, may be trying to push the part down into the parallels or into the vise. But let's just say for worst case analysis, for if you're trying to understand, do you have enough frictional force? Do you have the ability to create enough frictional force to keep the part from flying out of the vise? Right? So this is going to come up, especially with certain materials, right? So materials that have a low friction coefficient with the vise jaw material. So say you wanted to cut a part out of Teflon. One of the things we love about Teflon is it has a very low friction coefficient compared to everything else that you rub it against. Friction only matters when there's rubbing, right? Okay, so let's say we wanted to cut our part out of Teflon. And we wanted to understand before we started, are we going to be able to provide enough frictional force to keep the part from flying out? What do we have to do in order to understand that? If we're modeling the process before we get started.
Well, you need to know what kind of normal force we can apply to the Teflon with your vise.
Thousands and thousands of pounds of force. Because we got a giant mechanical advantage. So we can probably apply enough force, but what happens? We get a modulus of elasticity. That Teflon changes shape, right? And we saw with that example problem, when it changes shape, if we machine it, then we let go of it because we relieve the stress, the strain gets relieved, and it changes shape again. So it won't be the shape we want. So if we want to minimize the amount of that compression, but we want to maximize the holding force, and we're stuck with the material we have, and we want to model this before we get started. So we've got to make some assumptions of how much power it's going to take to make that cut, right? And we can do that if we have the unit power for Teflon, right? Because then it's just pull the numbers out of the machinery's handbook. So we want to make some assumptions about how much power it's going to take. Then we're going to assume that all of that power goes into the cutting force that's going to push it in a direction that's going to move. In reality, not all of it's going to go that direction. Some of it's going to be pushing, some of it's going to be trying to push it against the vise jaw, while some of it's trying to push it along the vise jaw, right? In reality, it's never going to be all lined up in the bad direction. But we assume when we do this model that it's all going to be lined up in the bad direction. So we can estimate the power. Once we've estimated the power, we turn that into force, right? How do we turn power into force? Right, because we said that power equals force times velocity, right? What's the velocity? Right, so that's our surface speed. So the velocity we care about here is our surface speed. How do we know what the surface speed is? Well, we know what the surface speed is because we choose it. Because we control the speed of rotation and we know how big the tool is. Right, so we get to choose the surface speed. We know what our surface speed is. We've estimated the power. We can figure out what the force is. Now we can figure out how much frictional force can we possibly establish based on knowing the material of the vice jaws and the material of the workpiece, right? Do we need to know anything else? What's frictional force equal? U times normal force, right? Right, mu is the friction coefficient. We can look up friction coefficient between plastic and steel. If we can't look it up, we could get an inclined bench and we could calculate it, right? All we need then is a protractor and somebody with good eyes to note when it starts sliding. So we can figure out what the friction coefficient is between our workpiece and our material. So then how much clamping force do we need to apply in order to keep the part from flying out? Yeah.
Mu times E over V.
Well, we don't have to keep it in terms of V over here, right? So our normal force, so friction, those two need to be equal. This is our cutting force, FC. F friction in vise. Not to be confused with the friction of the chip sliding on the rake face of the tool, right? This is just friction in the vise. So if these are equal, or if this is greater than that, then it won't throw the part out of the vise. Is that correct? And so F equals mu times N. What's that? Yeah, so it's got to be equal or bigger. We know that not all the cutting force is ever going to be pointed in a bad direction, right? So we're estimating, but yeah, this you could make this one be greater, right? That's the alligator eating, right? The alligator mouth opens up towards the bigger number. I have little kids, right? So that has to be. So we can figure out if we know the materials and we've picked our cutting speed, we can know the power, we can find the force, we know mu, we can find out what the normal force must be in order to hold the part in the vise. Right, you guys can all do that. Okay, if you find out what the normal force must be to hold the part in the vise, then you can look at the elastic modulus of the part and you can figure out how much you're going to squish the part with that normal force, right? And you're going to be able to model, if you have to have that normal force, can you make the part within the tolerances that you're asking for? Now, is it going to be predictable how much it squeezes? Is it going to be pretty much the same strain every time? As long as we tighten the vise the same amount every time, it's going to be pretty much the same strain every time. What could you do to make your part be the right shape?
Change the original model.
Or the tool path somewhat, right? You can modify the tool path so that you get a part that's the right shape after you let go of it instead of while you're holding on to it. And with stuff like Delrin or Teflon, plastics like this that are easy to squeeze, you have to do that sometimes. I wonder if anybody does it mathematically or if everybody just tries. I've never done the math. I believe there is math. that would let me figure it out. I've always just tried. And you try by backing off the clamping force sometimes. You try by changing the shape a little bit, maybe make it, if you're trying to get a circle, make a little bit of an oval. Yeah, okay, but we can all do this, right? Okay. What else did I want to review with them before we moved on? Vice jaws. So this is vice jaws, right? What if it was in a lathe, and you're looking end on the lathe, and you've got your 3 jaws, and you've got your workpiece in here. So we're looking straight at so here's the lathe chuck. We got our workpiece here. At some point when we're doing our turning operation, we're trying to push that workpiece back into the chuck, or we're trying to pull it away from the chuck, depending on what operation we're doing. So we're either trying to pull the workpiece out of the chuck or push it into the chuck when we're cutting. Right? We could do the same kind of math to estimate forces. And we could do the same math and to figure out what our normal force needs to be. What complicates it in a lathe? It's not because it's not the same in a lathe. It doesn't make that much difference if it's 2 here or 3 here. The real problem is that in order to do the cutting operation, that chuck is spinning, right? So the chuck is spinning, which means these pieces of steel that we're squeezing together with hydraulic pressure at a constant pressure are accelerating. In what direction are they accelerating? They're accelerating in this direction all the time, right? So what do we call that? Centrifugal, centripetal? I never remember. The physicists say there's one word we're supposed to use and one we're not, right? But there's an inertia. There's a force that's trying to pull it away, right? So you got to know the mass of these and how fast it's spinning. How fast is it spinning? Whatever the RPM is that we set, right? So if we know the mass and we know how fast it's spinning, how fast are they accelerating away? mv squared over r, right? So if you do the same thing in a lathe, you got to figure out how fast are the chuck jaws trying to get away. It's not as bad in a collet holder, but the collet is trying to open up also. Those are the things that I think we didn't cover. Oh. John says everybody got many people got the cantilevered beam problem wrong. No, we did it in a quiz, didn't we? Didn't we have a quiz where you guys had the cantilevered beam? Yeah. You just didn't have it in your group assignment. Tool life. Yeah. Did everybody get tool life wrong? A lot of people got tool life wrong on the quiz that we just did. Right. It's not. So when you do that graph where you got a straight line, where this is speed, right? And this is life. This is log 10, log base 10, log base 10. And that's why it's a straight line interpolation, but it's a straight line interpolation of the logs for the tool life question that people got wrong. Okay. I think that was the stuff we wanted to review before we got started. What are we talking about today? Anybody remember? Maybe look at the schedule to find out what today's lecture was going to be about, so you could read up on it beforehand. You know what I was doing just before I got here? I was searching for a funny video on YouTube about today's topic. There was one term that I vowed that I would show a YouTube video in class, every class. I didn't vow to do that with you guys. And I found some videos that were kind of funny, but they were really funny just because they were like, did you guys ever have the real movie players in school, or were they done with that by the time you guys went to school? Anybody? One person?
We had the movies.
You had the movies?
They were on VHS.
Okay. So it was one of those old-timey instructional videos to teach you about today's topic. But it was only funny because it was old-timey. It wasn't funny because they did anything funny. I regretted that. It would have been more fun to have a funny video to start off today. What are we talking about today? Anybody? Anybody? Ferris? Bueller? No? All right, you guys got that movie joke though, right? Okay. Because you don't always get my movie jokes because I watched movies a long time ago and some of you weren't born yet. Um, Anybody? Nobody? Did you know that there was a schedule that said what we were talking about today? Who knew that there was a schedule? Okay, you're not even ashamed that you knew there was a schedule and didn't look at it. So I could talk about anything, you wouldn't know. All right, so last summer, what did you do on your summer vacation? Well, it doesn't show on the screen, does it? Now, does anybody know what we're going to talk about today? Design for manufacturability. Right, DFM. You get the idea. Design for manufacturability. What do we mean when we say we want to design something for manufacturability? And so we're also going to spend some time today talking about design for machinability. But DFM in general means design for manufacturability. What does that mean? And why do we care? Yeah.
It kind of ties back into, dude, how are you going to make that?
It does kind of tie into, dude, how are you going to make that? Did I ever tell you the story where that came from?
Briefly.
Briefly?
I think it was like
It was an MQP group. Wayne was sitting in the MQP meeting where they're presenting to all the advisors about their designs, and his group mate puts up a picture of the front steering knuckle for the car they're going to build, and Wayne stands up and says, "Dude, how are you going to make that?" Just like that. It was great. Don't do that in the MQP meeting with your advisors there. Do that at the meeting that you had before the meeting you had with your advisors, which means you should be having a meeting with your group before the meeting you have with your advisors. Right? Advisee. You have to come to class, right? I would notice if you weren't here. I have a funny story about that too, but I'm not going to go into it. Design for manufacturability. What do we need to think of? So this is whose job is design for manufacturability? Yeah, it's the designer's job, even though it really impacts the manufacturer. But it is totally the designer's job to design for manufacturability. So if we're going to design for manufacturability, what are the kind of things we need to do? Yeah. We might want to think about how the part is going to be held when it's manufactured. So how it's going to be fixtured. What else are we going to think about? Yeah. Before you can even do the fixturing, you have to think of what processes are going to be used in order to make this thing, right? What else do we want to think of if we're thinking of design for manufacturability? During the manufacturing process, right? So what kind of, if we're doing a cutting operation, what kind of cutting forces, and is the part going to be strong enough to withstand them? That the same MQP with Wayne. Yeah, same MQP. They got some blanks, some aluminum blanks for wheels, and they were motorcycle wheel size wheels. And then they cut out basically the spoke pattern that they wanted to have on their wheels, or they left the spoke pattern that they wanted to have. And so they bolted it down to the bed of the machine tool, and then they cut through it and they cut around and they dropped out the pieces they didn't want to have in there. And man, was that loud. Why was it loud? Somebody in the back. Why was it loud? I mean, hellaciously loud. You could probably have heard it in this room when they were cutting it over there. Why was it loud? Somebody in the back. People in the back don't care. Why do you think it was loud? Blue hoodie thing. I forget your name.
Dawson.
Dawson. Why do you think it was loud?
I know. Repeat the. Like,
So we got a thing that looks like a motorcycle wheel, except it's a solid, well, not a solid piece of aluminum. It's like shaped like a motorcycle wheel, except for the center part doesn't have any holes through it. And they're machining that. They get it strapped down on the table. It was loud because it's the same shape as a speaker. They were vibrating a speaker with their cutting forces. It was really loud. Okay, so you want to think about the type of operations you're doing, the type, how much force there's going to be on it when you're doing that. Is the part itself going to be strong enough to withstand the cutting forces? You guys have made a couple parts in the lathe with a cutoff operation. Did you notice at the end of the cutoff operation, the part always falls off, it never cuts all the way through? Why is that? Yeah. Well, that's why it falls down instead of up, yes. Well, what makes it just fall off, though? Why doesn't it stay there until you cut all the way through? You got it?
And the little bit of material that's left isn't strong enough to.
Exactly. Eventually, the cutting force from the cutoff tool exceeds the strength of the material, and it just fractures, and it breaks off. So you'll never, ever cut all the way off without leaving a little nib like that from the cutoff operation, unless you hold the part from the other side while you cut it off. If you hold it on both sides when you cut it off, you can do that.
what if you feed it slow to the point where you barely have any cutting forces, but by the time it gets to center?
Well, I'm going to feel free to say you will never have no nib, but you can make it smaller. But I'm going to still feel free to say that it'll never go away entirely. They also make tools that are designed to minimize the size of it. Okay, so what else do we want to think about when we're designing for manufacturability? What do you think the most time-consuming part of most manufacturing processes is? So it can be, especially for a short production run. But if we get beyond setup, and somebody asked me about setup at the end of class too, I want to review some of that stuff too. But so if we have a long production run, the setup kind of gets lost in the noise. So let's assume we're doing a long production run. What do you think the most time-consuming part of making a consumer product that we're manufacturing is? Typically, not always. It's beyond that. It's actually the assembly. So we most things that we sell are made up of many components, right? And so we make these components, we make these components, we make these components, then somebody's got to put those together. So one of the longer time things in manufacturing can be the assembly process. So how could we make it so that we're designing for manufacturability when we're thinking about assembly? So design for assembly. What are the kind of things that we want to do? What could we think about? Yeah. So if things can fasten or come together easily, that's good. So you guys know what fasteners are? Is anybody in the room that has not used the word fastener before? Anybody? Can everybody say fastener for me right now? 1, 2, 3, fastener. I once had ME seniors, WPI ME seniors, arrive at the facility with their design asking for help for manufacturing. In the design, there were 2 parts. There were holes through the 2 parts. Clearly, you were going to put the 2 parts together and fasten them together. Without knowing what the design was for, you could tell just by looking at the pictures that clearly these 2 pieces were going to get fastened together. So my colleague was meeting with them, and he said, what kind of fasteners are you guys going to use? They were not foreign students. There was nothing lost in translation. These were grew up in America students. They did not know the word. Well, they did not know the word. They said, what? What's a fastener? We said, like nuts and bolts. Huh? So he goes over to the drawer, and he pulls out a fastener, And they said, oh, you mean screws? So they knew what screws were, but not nuts and bolts and not fasteners. And they were seniors in mechanical engineering here at WPI. So now everybody here knows that nuts and bolts are fasteners. What other kind of fasteners could we have? Velcro, retaining rings, pins,
Oh, what,
snap rings, rivets, zip ties, duct tape. Duct tape's a fastener. Holds race cars together, doesn't it? Except they call it speed tape, I think. All right, so let's talk about fasteners for our design for manufacturability. What do we want to do with our fasteners? Yes.
Probably want to keep them all the same.
All right. If we have fasteners, let's keep them the same. Kepi. Keep. Same. What would be even better than keeping all the fasteners the same? So there is design criteria that says make sure they have sufficient strength. I don't think it comes under the design for manufacturability, except if we're trying to keep them all the same, and we've decided that the fastener of choice is a 632 machine screw, and then a 632 machine screw does not have sufficient strength for part of what it needs to do. So you do need to be conscious of it. But let's leave it off our list for DFM for now. What else? Keep same. Don't use many. Somebody leaving in disgust? Don't use many. What would the ideal number of fasteners be? Zero would be the ideal number of fasteners for design for assembly. Because what do you got to do with fasteners? You got to pick them up. You got to touch them. You got to put them in the right place. You have to operate them, actuate them somehow, right? You know they make quarter turn fasteners, screws where you only have to make a quarter of a turn for it to be all the way tight.
That's horrifying.
Depends what it's holding. What about who's ever taken a door panel off a car? These fasteners there, right? And they just pop together. They're not really intended to come off, I guess. They don't want you to. All right, so 0 would be the ideal number of fasteners. Don't use many. Keep them the same as possible. Sometimes you need more than one fastener, but reduce. So what about the fastener to keep the same? So if it's a threaded fastener, you want to keep the threads the same, right? So you only have one fastener to pick up. You also want to keep the other end the same, right? So you only need one tool to put it together. All right, what else? Anything else designed for assembly? I think that covers fasteners mostly. We'd rather have things that pop together than things that, oh. All right, but glue is a fastening method, right? Would you like to use glue in your design for manufacturability? You said no, why not?
Well, because it means that we'll never, ever be able to, you know.
It makes it hard to take stuff back apart for maintenance. Sometimes that's not an issue. What's that? So, sometimes not being able to take it apart again isn't really that big a deal. I'm not saying that they got it right, but sometimes that's not a big deal. Sometimes you don't care as the manufacturer because you'd rather somebody buy a new one than repair the one they have, perhaps. What else don't we like about glue? Yeah. Usually you have to wait for it to dry. What else don't we like about glue? There could be, but there could be inconsistencies in our fasteners too, so we can get a quality glue supplier. Sometimes it dries before we wanted it to. It has a shelf life. Most glues have some sort of volatile element in them that off-gases, which smells. Sometimes it has enough of it that it's a safety hazard for the operators. A lot of glues have things like toluene and acetone in them and stuff like that. That's bad stuff. You don't want to breathe that. So yeah, we'd like to avoid glues if we can. All right. So fastening. What else do we want to think about with our design for manufacturability for assembly? Right now we're stuck on assembly. What else do we want to think about besides fastening? What are the chances of the operator doing it wrong, the assembly person doing it wrong?
Find parts that they only go in one way.
Design. So in the lean term for that is poka-yoke. Poka-yoke. I think that's how they spell it. Might be an E instead of an I. I don't think that's how you spell it, but it's called. Could you spell it? You speak Japanese, right? Key. Yeah, that looks better. There's an E at the end too, right? There, that's poka-yoke. That is designing parts so they only fit together in one way. So if you got to put these two things together, make it so you can't put them together, or make it so it doesn't matter if you put them together backwards. That works too. What about if we've got two side pieces on our thing? Let's make the two side pieces exactly identical to each other so it doesn't matter which side you put them on. Right? What else can we do? Let's pour out some ideas. What are we going to do to make our design more manufacturable for assembly? Make it so you can't put the parts together wrong. So how would you make something so you can't put it together wrong? Put a feature on it so that it can't fit the wrong way?
Like a locating.
Put a locating pin, put a locating slot. Locating pin, you might be able to put it upside down.
Right.
Two locating pins, that makes it harder. What else? What else can we do? We want to be able to assemble it quickly, easily. We want things to snap together, no fasteners, fit together only one way. What else? One more piece of low-hanging fruit here. Oh, this weekend I went apple picking. There was no low-hanging fruit. My daughter had to like stand on my shoulders to reach the apples. We got there late in the day. What else are we gonna do? Quick. Very low-hanging fruit. Number of parts. We would like a low number of parts. The fewer parts we have to assemble together, the more likely we'll assemble them together correctly. Right? We want to improve our possibility of success. We also got pumpkins when we went apple picking. And we got a little cart to haul the pumpkins around because we had, for some reason I have two kids, but we had to get 3 pumpkins. My daughter, 7 years old, says, talking about the wagon that I'm pulling the pumpkins on, she says, Daddy, how come it says #4 on the side of the wagon? The best part was when I told my wife didn't understand why it was funny. Because she doesn't do social media. All right, poka-yoke. All right, what else? Anything else? Reduce the number of parts. Yes?
There's no elegant way for me to say this. Avoid the destroying button. So don't, like, it's a house of cards. Don't build it like a house.
Don't build it like a house of cards. You guys ever built a house of cards? What happens when you pull one out at the bottom? The whole thing falls down usually. You build good houses of cards, right? But yeah, don't make it so that there's like one last thing that has to make it stick together.
That's the destroying button.
You pile all these things up. You got your foot holding something. Who's ever done assembly of something and had to use their foot to hold something in place while they were doing something else? Yeah, a lot of us have, right? You get maybe it's like a game of Twister, or now they get that paint yoga stuff. I saw it on the news yesterday. You get put finger paint on your hands, and then you do all these. I guess it makes artwork. You get all covered with paint too. Twister. What if you make several products that are similar to each other? Could you have components that are the same between those several products?
Yeah.
Do that then. Use standard components. Oh, we had a couple years ago, a student comes into the lab, and they needed to make a device where if they turned a handle, it would squeeze 2 parallel surfaces together.
That's advice.
And they needed to make it for the research that they were doing because they needed to be able to squeeze two parallel surfaces together, and they needed to be able to unsqueeze them and then squeeze them and then unsqueeze them and then squeeze them.
Did you give them a bite?
We made them buy a vise. Almost always, if there is a off-the-shelf manufactured component that will fill your need, it is almost always cheaper to buy the part from somebody else than it is to manufacture it in-house, if it's for your assembly. It is a bad engineering decision almost always to decide to make the thing because it'll be cheaper if we make it here. Because unless you're set up to make those in mass production, a commodity item, almost always cheaper to make outside. I say that, but then I know companies that all night long will make screws on a screw machine for their assemblies later on. But it's because they weren't using that screw machine for anything else and they owned it.
Well, F1 teams make their own bolts.
Sometimes there's quality reasons to do that too. Design parts to be multifunctional, multi-use parts. What else we got? Ease. All right, so design for ease of fabrication. What time is it? Good. Yeah, we covered. Oh, another one that's interesting is minimize the amount of handling that you need to do. It gets back to the House of Cards idea here. But if you got to take apart and then flip it over and then put it on its side and then put it on this side because you've got features coming from all different orientations, and this gets more to fabrication. This gets more to the part of where we're making the components as opposed to assembling the components together. The fewer number of setups that you need to do, the cheaper the part's going to be. Does that make sense? Fewer times you have to handle the part, the cheaper it's going to be. Maximize compliance. You guys know what compliance means in engineering terms? It's not about following the rules, although we would like you to maximize your compliance of following the rules also. I don't really care. But compliance in engineering terms means how easily things will slide together. So if you're going to put something into a fixture, does it locate itself into the fixture? If you're going to, we talk about compliance a lot in robotics engineering, especially we're talking about using industrial robots where we've got to pick something up, move it over, put it down. And it's how easily can we, how roughly can we know our location and still succeed in putting it in the hole? So if you've got a chamfer at the top of the hole, it will guide the pin into the hole, for example. If the gripper that's holding the thing has a little bit of springiness in it, and you're off a little bit in putting it in, it'll still fit in the hole. So another way to fasten things would be to do a press fit. You guys have heard about a press fit before, a force fit or a press fit? So there's a trick when designing something for a press fit. Because what happens, who's ever done a press fit, tried to press a bearing onto a shaft or put a bearing into a block and had it be a little bit crooked when you pressed? Yeah? That's a pain. It's a pain to fix too, right? And it can ruin the bearing very easily. So if we look at a cross section here, we've got our bearing hole. So say we're pressing the bearing down here in our cross section here. And so if it's a press fit with a bearing, which going to be bigger? So this is the bearing, this is the hole. If it's a press fit, which part's going to be bigger? The bearing. It's going to be a little bit bigger. In fact, on Thursday's lecture, we're going to talk about tolerancing and GD&T, and we're going to talk about how to determine how much bigger it needs to be, and how to determine how much force it will take to press it in if you know how much bigger it is. So the bearing's got to be a little bit bigger. So when it gets in there, it expands this material out a little bit, and it holds it in place, so you don't need anything else to hold it. Now, if you make at the top of the hole a little bit of a slip fit for the bearing, now when we're bringing our bearing, and this is a design for manufacturability tool here, when we bring our bearing over, it slides in, and now it's aligned with the hole, And we can press it down with our arbor press or whatever tool we're using to press it in place. And then the bearings always go in. They always stay straight. So you may have noticed on the base for for our thermoacoustic engine, there's that hole, the pocket at the back end of it that's got 3 little lips in it. That's because you can take one of those cylinders, cut it in half, press it into that hole, and make an alcohol burner to fire your Stirling engine with. And the reason we have 3 steps instead of just 1 step, like I showed here, is because we aren't that good at controlling the outside diameter of the cylinders. Because we don't try to control the outside diameter of the cylinders very much. But that's why that feature is on that part, because you can make an alcohol burner. There's no time to do it during M1800, so we don't. All right. How about design for machinability? Now we're going to do the machining stuff. What do we care about when we're doing our design for machinability? Yes. Fixturing. We got to care about how we're holding the part. We got to care about how much we're squeezing the part. We already talked about the fact that we don't want to have it in the vise in 15 different directions, right? So if we minimize the number of setups, we maximize our probability of success making the part. What else? What are things we want to be concerned about? Yeah.
Design parts to actually work with the machine tools you have, so don't create features that require a 3-axis mill or a 5-axis mill if you don't have that mill.
Yeah, I think that was what Wayne was complaining about with his project partner, is we didn't have a machine that was easy to set that part up in. It's also possible that he drew surfaces that it was impossible to reach. So can your tooling, is your capacity such that it's possible for a tool to reach the feature that you want it to make? That gets less important if you're additive manufacturing, but it's still important in additive manufacturing. Is it possible to, so when we're looking at our additive parts, how big is the span that you have to bridge? Things like that are important. If it's an FDM printer, then what's the alignment going to do, and how does that affect strength? I did an MQP a couple years ago where they actually were able to model the strength of FDM printed parts based on knowing the orientations and stuff like that. He made a bunch of test specimens and broke them. It was pretty fun. What else do we want to watch out for? There's a list of stuff in the PowerPoint presentation, but it's boring to do PowerPoint. What else do we want to look out for? What about long, skinny features? What do long, skinny things do? Like guitar strings? They vibrate? Thin walls are harder to make than thick walls. Trick for thin walls is leave a lot of material for the last pass. Don't try to do a finish pass on a thin wall. Leave a bunch of material, because then that thickness of material in front of your cutter is still supporting the wall. Whereas if you come back in and try to touch the wall to get that just a little bit thinner, it's going to vibrate a lot. Deep holes. Deep holes are difficult for a lot of reasons. Deep holes are difficult because it's hard to get the chips back out. Deep holes are difficult because the strength of the drill goes to, what's the deflection thing, right? And there's a length term in the deflection thing. And the length term is cubed. Yeah. And then the radius term, when we do our I for our moment of inertia for that, if it's a round tool, the radius term is to the 4th power. So the radius is important, as I go on the top or the bottom of that equation. I think it's on the top. So a bigger radius will deflect less, right? That's the radius of the tool, the diameter of the tool, radius of the tool. So the fatter the drill is, the less it's going to deflect. That makes sense? The skinnier the drill is, the more it's going to deflect. What happens if it deflects too much? It breaks. What happens if it deflects a little bit? If it deflects just a little bit, the hole on the top and the bottom won't line up with each other. And it'll do this through the part. What if you have to have a long, skinny hole? What if it's real small diameter? Pecking can help. I've seen so they make through so what we got trouble getting chips out of the hole. Pecking helps get the chips out of the hole, and it also doesn't necessarily help make the hole go straighter. Although if you are pecking with a long skinny drill, you don't want the drill to come all the way out of the hole at the top. Um, they make special drills for making long holes.
Oh, what's on the video presentation?
Where's the video? There it is. So it is possible to make long skinny holes. And they use specially designed drills called gun drills. What do you think they invented gun drills for? Making gun barrels. And I don't mean like a 6-shooter. I mean like a gun barrel on a ship. Or a howitzer, a cannon barrel. That's when they talk about gun barrels, they're talking about barrels there. I was actually at the Watervliet Arsenal, which is just up here in Watervliet, New York, a couple years ago. And they were making gun barrels, 30 feet long. They take a gun drill, and so I don't know, yay diameter, something like that. They take a gun drill, they drill it down the center of that 30-foot long piece of steel that's forged and hardened hard. And when they do that, it actually bends the workpiece. It becomes not straight. Now, it's problematic to have a gun barrel that's not straight. So then they put it on a special roller assembly that can roll it around. They get a dial indicator, just like we use in the lab over here, and they go back and forth on it as they're rolling it around. And they see how it's not straight. They've got a big piston ram that they bring over. They push down on it, and it flexes like this. You see it move about a foot in the center, 30 feet long steel tube that they just gun drilled. And then they back it off, and they measure it again, and it's straight. Because the guy that does that is an artist, and he's really good at it. I think they're going to have trouble when he retires. It's hard to teach people that. All right, so is the tool available? Can you get them? Diameter to depth ratios. You don't want to exceed a lot, or you don't want to have a high diameter to depth ratio in these holes, in general. But what else could you do if you had to have a long skinny hole?
If you're machining from the other side of the workpiece, could you come up from the, like you have?
You could drill from this side and drill from that side. You can flip the part over. It's hard to get those holes to line up, but it's not impossible. A lot of times you don't need the long skinny hole for the entire depth. A lot of times you could drill a bigger diameter hole for most of it and just do the end of the hole long and skinny, which doesn't give you as much deflection out there. So, and then it's especially nice if you can flip it over to do that. Okay, design for manufacturability. There's some more stuff if you look at the PowerPoint presentation. There's some other slides that have some stuff on them. Thin walls, yeah. There is no scheduled lecture for tomorrow. However, there will be a help session for people working on Group Project 3 in Washburn 229. And make sure we bring the microphone this week for the help session.
A lot of assumptions. Some assumptions are the wrong assumptions.